I'm the Vice President of the Young AFCEANs for the Central Maryland chapter. Today we've got technology over bagels with Nvidia. I also happen to work for Nvidia. I'm the account manager for DISA and Cybercom over here. We have Matt Penn, who's a senior solutions architect on the team. Matt is really good at describing cyber, and there's a lot of exciting things coming on over here at Nvidia regarding AI and cyber. So, I was really excited to share with this community some of the things that we've got going on. Also want to say thank you to Tensley Consulting for supporting our ongoing efforts. And, a couple of housekeeping items. I'd like to hear everybody's thoughts about going to a hybrid version of technology over bagels. So if you want to email me or just put in the chat, we're looking at either going to Tensley or Praxis and having these halfway in person again. You can either come, the speakers can either come, there'll just be a mix of virtual and in person with bagels again. And then, make sure you check out AFCEA Central Maryland's LinkedIn page and like and follow for all of the events that are going on. We've got some good ones coming up here soon. There's a social. The socials, we're looking to maybe go in person here soon as well. And then our next luncheon is going to have Lieutenant General Skinner from the U.S. Air Force and the commander of DISA speaking on his vision for DISA. And he'll have some things that will be that are of interest to him will be presented today, actually. So feel free to reach out to me around those things. And without further ado, Matt Penn.
Hey, thanks, John. And to come clean here, I guess I'm not eating bagels, but I wish I was. So it's a clever name. But anyway, my name is Matt Penn. I'm a senior solutions architect at Nvidia, and I'm excited to walk through some appropriate cyber technology this morning.
Awesome.
So today we'll cover kind of cybersecurity as a data problem, how Nvidia kind of views it from our lens. And we'll walk through a history of GPU accelerated cybersecurity. We've been thinking about this problem for a long time and have been in the business of accelerating data analysis for a long time. And then bring it all together by introducing Morpheus. It's a framework that was introduced during our recent GTC conference. And it's really the culmination of all the technology that we'll talk about here today.
Awesome.
So let's get started. We've got a lot of content, and it's going to be great. So to kind of kick things off, cybersecurity is one of those fields or domains that has a tremendous amount of data. The rates of data that are generated are tremendous, and they're heterogeneous in nature. All right, we've got computer networks, we've got bring your own device policies, we've got HPC high performance computing data centers, we've got just this crazy environment, and our security operations teams are charged with making sure that the networks remain safe. It's been estimated that it takes about 200 days to detect a breach in a network. That's just to see if something happened, and then another almost 70 days to contain a breach. And when you're working through this process of discovery and containment, your teams are working these rapid iterations to try to discover what has happened or to mitigate the problem, and it's really an onerous process. And if that wasn't hard enough, there's a persistent global shortage of professionals in this field, and unsurprisingly, with a shortage, you have an increasing number of breaches, and we're logging everything these days. We're in the big data era. We have been for some time, and we're collecting logs of all of our systems that are running. and we can't always analyze all of these. We certainly can't do it manually, and it's becoming increasingly apparent that we can't analyze all of these with classical computing techniques. Then lastly, there's some great vendors out there that are putting solutions out there to take bite-sized chunks out of this problem. However, our shortage of professionals that are already having trouble keeping up are seeing that it's difficult to learn all of these new tools. So something different has to happen in order to move the needle. This is a bit of an eye chart intentionally. It's a bit old. It would be even more of an eye chart today, but this is just to show the magnitude of all of the systems that are available today. That to really show how much our limited professionals are being charged with learning. So we're going to transition a little bit into what can we do about it? And we're going to walk through a little bit of the Nvidia kind of open source technology story, things that we've been working on for the last few years that we've made available to the world for free to try to tackle some of these problems. But first, it's important to kind of understand why GPUs, right? Why parallel computing? Why does this make sense? And for a number of years, for many years, decades, single-threaded performance was improving by 1.5x every year, and this was great. But in recent years, this has really tailed off, and we're not seeing the same year-over-year performance improvements. And that makes it really challenging to take on problems of the magnitude of cyber and many others. Fortunately, with the GPU, it's technology that Nvidia invented. We've built a chip that makes it really, really easy to throw a whole bunch of cores at the problem. While with your CPU, you may have single digits, if you're lucky, double digit, independent cores running on the chip. With a GPU, you've got thousands of these things, right? And if you cast your problem properly, you can leverage all of these to crunch a lot of numbers really, really fast. And in the advent of GPU computing, we're still seeing this, year over year, 1.5x improvement in performance, which makes it possible to tackle some of the problems that we'll talk about today. And just to level set, we're going to talk a little bit about some popular bins that are important to think about when talking about cyber data analysis, whether that be AI or just data analytics. And there are three big bins, and they're not mutually exclusive, but they're helpful to kind of think about the data problem. And, the first of which is HPC. It stands for high performance computing. And today, you may think about an HPC problem as a physics simulation, maybe a fluid dynamics problem, something that you would expect the national labs to be solving for. But those aren't the only people solving HPC problems. In fact, cyber, there are many cyber problems that could be cast in the HPC space. A lot of graph analytics happening. HPDA, this stands for high performance data analytics. This is what most of us probably think about when we think about data analytics, the dashboards, business intelligence, perhaps classical machine learning, things like this. And then artificial intelligence, where I'm going to, delineate between HPDA and artificial intelligence with things like deep learning. And, these each have tremendous compute demands and like I said, not mutually exclusive, but all perfect for this, this GPU framework. Like we can take care of all this parallelism that we've heard about, and we can do it in these three domains, and we can apply it to the cyber problem. And there are going to be tools for us to do this for free today. But before we do that, it's important to think about, what are some best practices? Where are some pitfalls that I may want to look out for if I go from my traditional CPU computing with the tools I've used for years, and I want to transition to GPUs? Why did Nvidia invest in some new tool sets and release them to the world? So it's important to think about this. So we're going to go from left to right here. We're going to start with a traditional model. This isn't. This is probably what folks do the first time they convert an application to GPUs. They've got an application, say A and B, and they've been built for CPUs and they run great for a long time. And now all of a sudden you're running into some compute bottlenecks and you can't maybe serve your entire user base. So maybe you take a piece of your code that's, computationally intensive or is trying to do some machine learning, and you port that over to GPU and you're like, great, I've done that really fast. So you send the data from your CPU to your GPU and then you get it back and then your application goes on its merry way. And as time progresses, you do this a lot of times. And these arrows are actually bottlenecks that you're going to run into. You're sending data, the more you send data between the CPU and GPU, the more performance you leave on the table. And at NVIDIA, we're like, well, what's a way we can make it really, really easy for the community to update their apps, but not fall into this kind of I/O pitfall where they're leaving performance on the table. And I don't know, it might have been five years ago or so, give or take, where the Rapids project began. And what Rapids is it's an open source project. It exposes Python API to, for folks like data scientists, folks like me, and many across the world. And the API is the same as those CPU tools we've been using all along. So when I migrate my code over to GPU, I don't have to teach myself, some niche, language, from NVIDIA side, compute unified device architecture, CUDA. I don't have to learn low-level CUDA C++. I can just use the APIs I've been using for years, and I don't have to, write these inefficient, data transfers. It just kind of handles that right out of the box. So I'm like, oh, great! Now I can do everything I've heard about, and I don't have to, be a super performance engineer, and I can start rolling my application out with Rapids. This is a tremendous value proposition, and Rapids makes it really easy to do this. And it gets even better, right? So today, PyTorch on the left here is one of the most popular deep learning frameworks. And for those on the line who have at least heard people talk about data science, you've heard probably about NumPy, you've probably heard about pandas, you've probably heard about TensorFlow or PyTorch. And the folks that use those libraries can just move data between these frameworks trivially, through the NumPy array interface. And with this GPU ecosystem, we've introduced the CUDA array interface. So you can take your data that's in any of these formats and just move it to another framework without worrying about these copying data back and forth from the CPU and GPU. This makes truly an end-to-end, exposes an end-to-end capability to perform data science from prepping your data to training your model to visualizing it to testing that a bunch of times, and you're just natively implementing best practices. Here's a little bit of a different view of the same kind of thing. So if we go from left to right here, on the top row, these are the big buckets in any kind of data analytics task, right? Whether not even cyber, right? It's cyber, but not limited to cyber. The first thing you do is you get your data ready to analyze, and we're going to unpack this quite a bit later in the talk. You train a model. Your first model is almost certainly bad, right? And then maybe you visualize your results, and you're going to go through this process a whole bunch of times until you converge on the right answer. And as your data problem gets bigger, the less iterations you can really go through. And Rapids tackles all three of these, right? And if you look towards the bottom, these are the pieces that are included within Rapids. It's not comprehensive, but talks about the larger pieces. Through DAS, we can distribute our workloads across many GPUs or many nodes with GPUs. This lets you scale out. Pretty analogous to your legacy Hadoop or Spark. In fact, today Spark 3.0 is accelerated by GPUs as well, using a lot of the tools that are built within Rapids. And throughout this process, we're not going to make extra copies of the data. Right? We're going to leverage the CUDA array interface that we talked about before, or something called DLPack, which is a very similar data structure. So we're going to do all this, and we don't have to think about it. That's the great thing. Like when you start developing, you're going to say, hey, what did Matt say? I don't have to think about that so much. I'm just going to use the libraries that I know the APIs for, and it's going to be great. So to make things a little bit more concrete, here's a mapping of some of the more popular CPU tools today that I've used for years and love, and their GPU accelerated counterparts. And again, all open source. So when your data problem becomes too big, it may make sense to try something else, and that something else should be a drop-in replacement with the same API. So for your pandas, you're handling your CSV type, your tabular data structures. cuDF has the same API as pandas. For those training classical machine learning models, k-means clustering, we've all probably heard of, k-nearest neighbors, XGBoost, right? You're going to use your cuML, which is going to have the same look and feel as your CPU equivalent. For those doing graph analytics work, a big task within the cyber world, I had used NetworkX probably 10 years ago and was running into bottlenecks. If I had access to cuGraph back then, I could have taken on my whole problem as opposed to just cherry picking pieces of it that I can solve within the time I had. And the list goes on. And again, the main thing to take away here is maybe not to memorize all of these, but to realize that there are drop-in replacements for these compute-intensive libraries that we've used. And the API is going to be the same, if not very similar, in the GPU accelerated equivalent. And the learning curve is going to be very flat. It's going to be very easy to on-ramp technical teams into using these new libraries. So I know the description of today's talk said it was targeted at beginners to intermediate to advanced, and I'm going to apologize to some of the beginner folks, but this isn't really designed to teach you to code. This is really just designed to show you concretely the similarities in the APIs. We're just going to take a quick peek at some code, and I promise we'll get back to the rest of the presentation. So here, when doing data science, the first thing you do probably is you read in some data structure, some data from disks, if you will. And the only thing that we're really trying to show here is for this toy data set that was maybe a couple million rows, we're getting 3.2x speed up over pandas, and these numbers are probably almost certainly faster today. And if you look at the code, it's identical. The only thing that's different is the name of the library, right? Read CSV dot file name. Look at the bottom row. Read CSV, file name. And the only thing that's different is the import statement. That makes it super easy to port your code to GPU. In fact, if I just imported cuDF as PD, my code wouldn't have to change in this example. I would just change my import statement. The next example, a little bit more on the line here, but the theme is the same, right? Here I'm doing an aggregate function, a count, right? I'm counting the number of things that happened within a time window. This is a popular thing that you would do, if you see a dashboard that's showing you, a total of something that's happening, something like this is happening behind the scenes. And if you look at the code again, you'll see it's identical, right? We're selecting a subset of our data and we're counting it, and then we're resetting an index, and then the API is the same here. And all the while we're getting 7.3x speed up on this toy data set. And these speed up values get more dramatic as your data problem becomes more significant. I think the last little code block we'll talk about today is it's just a few more concrete examples of the drop-in replacements and the import statements. So the first row would be the NetworkX. For your graph analytics problem, import cuGraph as CX. All right, I would use CX instead of NX in my code, and things are going to work. The next two lines, k-means, right? I'm literally importing the same library, so my code won't change in this case. And then the last one, which technically isn't part of core Rapids, but is part of the Rapids ecosystem, is a drop-in replacement for NumPy. Import as CP instead of NP, and you're off to the races. I can't tell you how many people that I've talked to about Rapids that heard about CuPy and their lives been changed forever. So I encourage you to look at these. So now we're gonna step back a bit, and we're just gonna talk about a day in the life of a data scientist. right? And again, these are all, we see the cyber problem as a data problem. So we're abstracting a bit here before we dive into the cyber bits. So the first thing you do is you classify your problem. You figure out what kind of problem I'm going to be solving here, first of all. And then, you say, okay, I'm going to solve this. I'm going to need this kind of data. So, maybe you have a network tap where you're saying, oh, okay, I need to write out these kinds of logs, these kinds of data in order to solve this kind of problem in the cyberspace. Then you process your data, you model your problem, and you validate your model. And you do this a whole bunch of times until you get something that works. And then once you have something that works, you want to scale that up. So you deploy that as part of your production application. And I'd like to, draw your attention here to kind of these, process data, model the problem, validate, execute. We spend a lot of time here, so get comfortable, and we're going to unpack this a bit. So here's just a view of really what's within those three boxes, right? So if you look at the left, you've got this, what your classical workflow may look like, CPU powered. You download your data, you start your data processing pipeline called ETL, extract, transform, load. You wait a long time just to realize that you did it wrong. And you're like, oh man, you restart it, you wait a long time, you realize you did it wrong. You restart, the theme, right? And then by the end of the day, you haven't really done anything meaningful. So if you had switched over to the GPU accelerated pipeline using the Rapids tools, it's free, you would have found out that your code's not working much more quickly. And by the end of the day, you've already started modeling, right? These green processing regions and these plots are very small now. And I'm not waiting. I'm doing meaningful work. And this is a tremendous value proposition and the basis for everything we'll talk about today. All right, so now diving into the cyber pieces, right? So we've got smart folks on our teams. We've got cyber domain experts. We've got perhaps cyber data scientists, and we know that there are fast compute options, and we know we have our existing SIMs or tools that we use for cyber. Think your Splunks of the world. How can we take these pieces and do something meaningful to take a bite out of the problem that we've outlined in the beginning? And everything we do at Nvidia we use first. So we build these tools so that we can. We have data centers. We power. Our supercomputers are among the fastest in the world. So it's on us to do the same kinds of things. So we build tools like CLIX, cyber log accelerators, to make it easy for us and those around the world to do the same kind of thing. So what CLIX is it's an open source project built on Rapids that includes a whole bunch of use case examples, workflows that allow you to build end-to-end processes and allow you to integrate with popular, enterprise tools like Splunk today. I always tell people CLIX is cool for two reasons. It's cool because it does something important on its own, but it also shows you an example of what you can build on top of Rapids. Right? So CLIX didn't exist before Rapids. Our team had Rapids and said, oh, it would be great if we could build something on top of Rapids that was specific for cyber. And that's what CLIX is. And it's really targeted towards our security operations center, teams, our InfoSec data scientists, folks like this, to allow them to be, bigger, faster, stronger with the same amount of resources. So like I said, included in CLIX are Jupyter notebooks. These are examples of implementations of solutions for specific use cases. We'll walk through a few of those today. They have documentation within there, kind of walk you through the steps. Integration with Splunk is included in there. We have an app that allows you to query Splunk long-term storage, and we have a brief example of that. Ways to stitch together capabilities that you that you build, so that you can deploy these into production more easily. And then, primitives like, we treat things like IPv4 or IPv6 as first-class citizens so that you can do your analysis on that easily. So kind of the first big thing, right, before you do any data analysis, you have to prepare it. And it's like the dirty old secret of data analysis is you have to do that. And log parsing is absolutely no exception. Any kind of cyber dashboard you've seen in your life has had to do this first. And you know, logs are heterogeneous. As we build custom apps for each of our organizations, right? We're generating new logs. These almost certainly don't have pre-built regular expressions to parse them. We have to build those ourselves. And as the data goes up, we can't parse these ourselves, or we can't keep up with the throughput. And then we have, you know, like the old, cell phone analogy, dead zones. And it would be bad if we had an incident where we didn't have data recorded or parsed properly for those events. So think about that analogy as we go through here. It's important again because the classic methods, they don't scale. Think back to the Moore's law chart. They're heuristic based, so you're effectively hard coding what you're going to do, and if anything deviates from that hard coded rule, you will be unable to extract that information. This is just so true with regular expressions. They can be painful to write, and they can be incredibly rigid. And if your log format, like the one we're looking at here in the bottom left, changes at all, your regular expression will fail. And as it turns out, you know, this may be a nice problem for AI to solve, right? So if we think about, you know, we may have heard of natural language processing. For those that haven't, it's the field of deep learning to learn the contextual information about the human language. And if you think about logs, they're a language themselves. There's contextual information in there. They're usually unstructured text, which is just like human language. And as it turns out, we can use the same kinds of techniques to get over this hump of rigid regular expression so that we can parse more data more accurately. And our engineering teams here at Nvidia and research teams have taken this on. And as actually part of those notebooks that we've released to the world, you know, we've made this specific example available for free. And we're just going to walk briefly through the process of what it takes to do this. So you have your raw logs, right? Whether you've got a network tap or you're pulling data from your syslogs on a specific machine or whatever, you pull those out. And the first thing you have to do is you have to turn words or logs into numbers. And this process is called tokenization. And we've actually GPU accelerated this piece as well and included that in clicks. The next thing that you do is you prepare your data for training, right? And we know regular expressions are rigid. So as part of this training process, this data prep, we permutate our training data a little bit. We change starting parts of logs. We degrade the training data, you know, through several routines like changing the order or dropping spaces or things like this, things that would break your normal regular expression. And then we feed this to a large BERT-based model. BERT is the state-of-the-art natural language models today, transformer models today. And then instead of training it on Wikipedia, human language, we're training it on logs, and we're specifically training it to perform a task called named entity recognition. This is taking this piece of the log and saying this piece is an IP address. This piece is a username, right? Our AI in this case will be able to parse for us like that. And then once you have this model, you would deploy it, right? You would deploy this as part of any data transformation pipeline, things that would be, writing data to your cyber database, things like Splunk is doing today to write data there. In fact, they're teamed with our cyber engineering team to deploy this kind of technology to accelerate, and improve the accuracy of log parsing today. The next piece that we'll talk about is integrations with tools like Splunk, case in point. So Clicks actually comes with an app that allows you to query long-term storage. You put your queries in, and you can immediately take advantage of all the accelerated rapids technology and CyberLog accelerator libraries that have been built to accelerate data analysis. Things that you may not be able to do out of box in your SIM, you can do by connecting these open source tools with your SIM. You've effectively extended your SIM to take on a broader set of capabilities. And it's just a high-level view of how this may work. You have your Splunk interface. You've got your Click search app that's integrated, and your search app makes an HTTP request that executes your rapid stack or your workflow here that's going to sit on top of clicks and execute these rapids queries and slicing and dicing and joining of your data so that you can do whatever custom task that it is that you need it to do. So the next section here, we're going to walk through a few specific use cases that were all built on clicks, and these are really targeted towards the cyber scenario. So the first one here is the code's not necessarily to show you how to code again. It's just to show you we're computing a ZScore, which is a simple way to implement an anomaly detection on data, specifically notable alerts that have been exported from Splunk. I think we have a couple million rows here, and we're just cranking through these anomaly detection calculations and G2 accelerating them across every notable alert. And this is included out of the box with clicks. It's something you could go home and implement today for free using the clicks library in Python, using those same APIs that you're familiar with. Pretty cool. The next one here is, it's the same kind of data set, but let's say you want to look across all of your alert types, right? And, you're getting alerts on a daily basis. Some of these are false positives. Here, I think we're looking at, 3.2 million events, again, exported from Splunk. And what we want to do here in the real case, it's going to be almost certainly orders of magnitude more than 3.2 million events, is identify a scenario where we've got a lot of weird stuff happening, right? This plot behind this kind of slick sheet view is think about like a heat map, right? Where we've got time along the x-axis and we've got alert types along the y-axis, and this bright vertical strip here is actually representative of when a system went offline and things were being upgraded. By analyzing all of the data in one shot very quickly in Rapids, we're able to see visually that, something really weird is happening at this time step. What's happening? Oh, we are in fact upgrading the system, and there were some false positives there. That kind of data fusion is bread and butter for Rapids. The next piece here is dynamic network mapping. All of us in the cyber world have almost certainly seen these huge spider graphs of networks, right? And in my past lives, I've had to spend a lot of time making this graph small before I could interact with it visually. The tool we're looking at here is not free in open source, but it's very useful. It's called Graphistry. It allows you to inspect these large graphs without your screen flickering and your computer choking, right? You can explore this kind of dynamically and filter it. Things that would not be trivial with kind of legacy tools. But the important part here is not necessarily the visualization, but the types of analytics we can run on large graphs. Right? We can run these calculations on large graphs across many nodes with many GPUs. Things like page rank, identify that maybe the most important nodes within a network. Things like personalized page rank, where I can see changes in nodes' importance with relative to other nodes within my network. I can perform things like community detection, and I can do all of these things very very often. Right? I don't have to run this overnight in a batch job. I can run this many times a day, right? Because I'm accelerating this whole process. In some of these tasks, I think specifically the page rank of example, we're seeing up to over 2,000 times speed up over the cost equivalent Hadoop Spark option, right? That really starts to speak to things that we can really start scaling out these analytics on our whole network. We can bring down that 200 days to discovery way down. And this kind of brings it all together for clicks, right? So we have all these discrete pieces, right? We've got these primitives, we've got these use cases that we've built, we've iterated a whole bunch of times, or maybe we're integrating with a pub sub framework like Kafka, right? And we are doing all these pieces, and we can stick them together, right? Clicks includes this I/O glue that allows you to wrap up each of these capabilities, connect them together into a workflow, and just deploy that workflow, right? I'm just going to deploy this workflow, and this workflow is going to represent my production, let's say, log parsing workflow, right? I'm going to wrap up my Cybert log parsing, deep learning log parsing capability in a Clicks workflow, and I'm going to deploy that. And Clicks makes it really easy to do that. That's really the end game, right? You want to find something that works, and you want to deploy it. And this makes it easy to do so. And I believe we'll be distributing these slides afterwards. I'll have to confirm with John, but the example notebooks link there is a link to the
everybody's email who registered for this, and
okay.
Yeah. I mean, whatever you want me to follow up with everybody on, just go ahead and send it over to me, and I'll kick it over to everybody that registered. Great,
that's awesome. So this will be useful then. So this is just I don't expect anyone to read this slide, but there's a bunch of Jupyter notebooks. These are screen captures of Jupyter notebooks, but what's important here is the green text on the left. This is going to take you right to those notebooks. So you can spin these up. If you've got a gaming rig at home with a GeForce card, you could spin these up there. If you're lucky enough to have large compute resources, you can spin up there. If you've got access to Google Colab, you could test some of these there. But anyway, I wanted to have the group here be able to test some of the ideas that we talked about today. So, we've talked about some raw materials as I characterize those, things that we've built over the years. We've exposed to the world. People are adopting this across industries. We use them heavily internally for our cyber processes. And as it turns out, since they've all been built to work together, and increasingly building on top of each of these forces the bottom layers to be efficient, it made sense to put them all together as a unified cyber framework, a framework that could be used to deploy AI to an enterprise. And if you went to GTC this year, if you listened to the keynote by Jensen, you probably heard Morpheus talked about. Morpheus is that framework, and that's what we'll talk about here today. And this builds on the problem that we introduced in the very beginning. Today, systems are implemented through microservices. These microservices talk to each other. They talk to other nodes. There's a tremendous, I think it's 80% of the traffic in your network is east-west traffic. Communication between nodes within your network. And roughly 50% of incidents are from insider threat, right? So now this zero trust framework is prevalent everywhere. But as the networks get bigger, there's no boundaries, right? We bring your own device, and the data problem continues to grow. And to do things like Cybert, for example, a language model to run on high data rate data sets, it requires a certain kind of compute in order to do that, right? So at Nvidia, we're like, okay, well, we have this, right? We have all these tools. Let's see if we can build a framework around this to really solve this problem for real. And before we dive into this, it's not always intuitive to understand how AI may apply to a cyber problem like this. So we're going to walk through a little bit of an analogy here first. We've almost all certainly gone through a traffic intersection, a traffic circle or something, seen a traffic light or a traffic camera, been captured on traffic camera and given a citation. But in this scenario, right, we're going to walk through three processes: perceive, infer, act. And the perception piece here is perceiving, like as us humans, we have eyes, we perceive the environment through our five senses. In this case, it'll be much like our eyes. And the currency of perception is going to be through a video feed effectively here. So in this scenario, our traffic camera is perceiving the environment through some amount of frames per second, images taken rapidly to understand what's happening. Now, we've probably all seen object detection demos, people detecting where faces are in a image, or where a car is in an image. This is called inference. This is taking a sensor reading, taking a model that you've trained to abstract information from the sensor reading here. So in this scenario, I may be perceiving the environment with a traffic camera. I may be running my object detection model to count cars, and I'm going to be able to estimate what's the throughput of traffic in this intersection at any given time, right? And then armed with this contextual information, I can make a decision. I can decide whether I want to change the frequency of red lights, or of traffic lights, patterns. I can make a decision to improve the infrastructure to make it safer for pedestrians, cyclists, and vehicles to traverse that intersection. I can do things with this information, and this is the same process we're going to follow with Morpheus. You can see those same three across the top. And so now we're going to talk a little about what Morpheus is. So in our networks, we so actually let me back up. So the idea behind Morpheus is to treat every node in your network as a sensor, right? The sensor this node can act independently, or it can aggregate these sensor readings to have a higher level picture as to what's happening in your network. And kind of the most performant way to deploy Morpheus is through the combination of what's called the BlueField 2 and something like an EGX server, which is a server with GPUs in it. Just for lack of a better word, a server with GPUs in it. And we're just going to walk from left to right here. So with your BlueField 2, think about it like a smart NIC with its own CPU cores on it. And what I'm able to do here is I'm able to do out of band tasks or analytics on my data. I am able to do this without taxing my host CPU. So all of these additional tasks that we're asking the computer to do, like collect these additional data, parse these additional data, I'm not wasting my CPU cycles on my host. All my production applications aren't going to suffer. So that's the key takeaway here. The second is we leverage what's called the Cumulus NetQ agent. You don't have to memorize the term. These slides will be shared with you. But what it does is it publishes network telemetry data in a pub/sub framework. And so let's say the example we'll talk about later is layer 7 application data. Right, so I'm publishing this to a pub/sub framework, and on the right here we've got a disaggregate or a decoupled inference framework, which is the core of Morpheus. And while we're collecting data on the BlueField, on the Morpheus side, on our GPU server, we're cranking through an end-to-end AI inference pipeline where we're taking let's say the application data, we're parsing it, we are detecting, let's say, sensitive information. And then if we do find it, we're publishing that back to this pub/sub framework. And then our BlueField, for example, can re-provision that server, change the policies on it. Or let's say we have I don't know, what's a good example? Let's say an HR system, right, that's supposed to be encrypting my PII. Let's say we roll a new production version of that and we're no longer encrypting that information. We can roll back to a previous version that we trusted. That can all be automated, that end-to-end process, or we could bubble these up for somebody to manually inspect and change these policies or roll back systems manually. But the idea here is if you look into this green box, you're seeing some familiar words, right? You're seeing pub/sub, that's a very popular way to implement decoupled systems. You're seeing rapids. Rapids is, we've been talking about that all day. Clicks built on rapids. Streams is a way to read data from pub/sub into rapids super fast. But what you haven't heard maybe is Triton or TensorRT. These are other projects that we've open sourced that make it really, really efficient to run big AI models fast on many GPUs and many nodes. So when we put all these pieces together, we're doing our data prep fast, we're running inference fast, and we're scaling this out, and we're able to handle many inference requests from our entire network at the same time. One of my colleagues was describing fielding roughly 34 of these Bluefield 2 SmartNICs with a single A100 GPU for that specific workload. But it's just the point, like, we're handling a whole bunch of network traffic. We're running these heavyweight models on it, and we're keeping up with the line rate for these use cases. And that's a tremendous feat, and it's something that wouldn't be possible if you weren't offloading your CPU to handle these things. And again, a framework to deploy this yourself. I guess I won't spend a whole lot of time on this slide, but this is just kind of a snapshot of those two types of chips. I'll draw your attention to the one on the left. This is coming soon. Think about a SmartNIC with its own ARM cores, but also a GPU right there. So instead of sending my network telemetry data to another server, I can handle everything right there on the same node. My node is going to be autonomous. If I detect the sensitive information, I'm going to adjust my policies out of band right there on the fly. And that's just a true game changer. And the EGX server on the right is just a server that has these SmartNICs as well as the GPUs on board. So you can do any combinations of the things that we've described. And then this slide abstracts a little bit further. It is a decoupled implementation. You don't necessarily have to use the NetQ agent to publish telemetry data. In fact, the Morpheus framework was designed to allow you to subscribe to any pub/sub framework. So if you've got your own, network data publisher out there that you want us to stick Morpheus on, you can totally do that, and why it's decoupled today. So this is just the general example. Let's say your SIM is publishing some kind of network feed, or you've got some application log server that you want to read data from. You could implement that kind of more general framework with Morpheus very easily. And the last bit here is we'll just talk through a concrete example. This is actually part of the keynote address as part of GTC. But this is that sensitive information leaking example. So each of these white circles in this slide represent a node in the network. The white lines connecting these represent, data being sent around that doesn't include sensitive information. If you look towards the top left, middle left, I guess, you see a white circle where you start to see red lines come out of it. This is an example of where sensitive information was leaked in the clear, where we may not have known about this. And by using Morpheus, we're able to detect this very quickly, see where this information was sent. And if you remember, roughly 50% of the breach is being from insider threat. Sending this information in the clear, even if you're on your own, private network, is still very, very risky and can result in terrible outcomes. And what's happening under the scenes here to implement something like that is, we walk through a typical training process. We pre-processed our data again with Rapids. Right, you should be getting some pretty good muscle memory now. We trained our data. We pre-processed our data with Rapids. We trained our model with a deep learning framework, and we deployed it to Morpheus. 1, 2, 3. Right. And then on the inference side, this is a little bit of a technical side, admittedly, but we've deployed this model, right? And we've got our sensor. The sensor's publishing this layer 7 data to a pub/sub framework like Kafka. Morpheus is pulling this data down from Kafka in an accelerated fashion. We're pre-processing this data with Rapids. We're building up a buffer, sending these data to an inference framework like Triton in batches. We're cranking through these inferences, and we're performing something like named entity recognition, like we're doing with log parsing, where we're saying, oh, this is maybe an SSN, this is a credit card number, this is whatever type of sensitive information it is, and then we're outputting that someplace, whether to file or to perhaps change a policy on a node, or to bubble that up to some analyst who's looking at a dashboard for looking for problems in network traffic. And that's kind of what's happening under the hood with Morpheus, is a plot much like this that would field any kind of use case. And the only thing that would change really is your model or your pre-processing steps. So today, Morpheus is out for early access. You can request early access today. The models that will be included in the first version will be leak-sensitive information, the example we just walked through, anomalous behavior profiling, phishing detection, and predictive maintenance. There'll be many others coming. The planned versions today are network mapping, asset classification, domain generating algorithm detection, generic lightweight online detection of anomalies. I think the ZScore, something more sophisticated. Those will be coming soon. But again, early access, you can apply today. The link is in the green text on the top. Like I said, we'll be sharing these slides with you. So if you go there, request early access, you can start playing around with these tools very soon, in the near future. And again, Clicks is available today as well. You should totally go and download that and get familiar with it. Once you taste the speed for the first time, it's kind of hard to go back. That was certainly the experience I had. I think that's my last slide. This is my last slide. If you attended GTC, there's the sessions are available on demand. Here's a few that you may want to look at. They're gonna unpack a few of these in more detail. You'll see some examples of other, members of the cyber ecosystem implementing some of these technologies. You'll hear how we do it. But John, I think at this point, that's my last content slide, and it might make sense to open up for questions.
Hey, Matt,
right.
it's Larry. I just thought I'd highlight one question in the chat. That was a great talk, Matt. That was really well done. Thank you. I just wanted to highlight one question in the chat. There were a couple, I think, that I answered, but there was a question about the early access for Morpheus, and I know you're working more closely with that team. So they were wondering, when will the early access actually, if they apply now, when would they expect to get access? What's available now, et cetera? Yeah, so I think we'll target probably summertime. Summertime would be what I would expect. I don't have a specific date handy. You all have my name. If you want to reach out to me on LinkedIn, I can answer that more specifically and connect with some of my colleagues. I apologize for not having a specific date today. This is all new technology, and we want to get it out in everyone's hands as soon as possible. But yeah, feel free to reach out, and I can get you the right answer there.
Okay, awesome. I think this is a pretty powerful slide too, because as a lot of people on the line know, Booz Allen does a lot within the Central Maryland area with all of our customers in and around Fort Meade, and Splunk as well. Splunk has the big ELA with the MPO customer. So leveraging these technologies to further bring better solutions to these customers is going to be great. So does anybody have any questions? You can unmute yourself and ask. We've been monitoring the chat this whole time. Yeah. Anything? Let me see who's on here. No. Mr. Sheldon, Mr. Fink. Okay, cool, awesome.
Here, John.
Hey, Brian, how's it going? Hey, so thank you everybody for joining today. I'm going to take the list of everybody that registered, and I'm going to send out the slides and YouTube video link to this session. Again, please let me know what people's thoughts are around in-person events. And again, tomorrow we've got a great Yak Social coming up that's going to be with the students of Empower Baltimore. And so it's going to be a great event, really promoting inclusion and diversity within, our Central Maryland STEM industry that we all work in. And then our next luncheon is going to have Lieutenant General Skinner, the new DISA, incoming DISA commander, and he's going to speak about where he sees the future of DISA going. So really appreciate everybody's time, and hopefully everybody here knows how to reach me at this point. Yeah, does anybody have anything else?
Yeah, John, I just wanted to just mention to everybody, if anybody else is interested in hosting a TOB and sponsoring and presenting, just let one of us know. That's about it.
Awesome. Thanks, Gary. Well, Gary, I guess with that being said, we can go ahead and end it.
Awesome. Great. Thanks, everybody. Have a good one.
Thank you.
Thanks, Matt.
Thanks. Take care.